All right, so today what we're going to do is we're going to look at one of the in-class problems from section 11.5. All right, this dealt with hydrated compounds, and the ultimate goal of the hydrated compound was to, one, determine how many waters there is, and then ultimately write the formula and name that particular hydrate. Okay, so we have lead 2 acetate that exists as a hydrate and is 14.25% water by mass. We want to know what is the molecular formula for this hydrate, and we're given the distinct molar masses in these problems. Now, a couple of things that I want to show you here. Number one, our ultimate goal is, hey, how many waters are out in front of this problem? The other thing is, in notes, we did not work with this 14.25%, or we didn't work with percent at all. All right. So I want to do a couple of things here. Number one, I want to just circle and highlight really the percent. Well, if we're given a percent, we're going to assume we have a 100 gram sample. Okay, that really gets us going in this problem, and that's 100 grams. I should say 100 gram sample total. So our first goal is to do this. We're going to, number one, determine our mass of water, and then ultimately determine our mass of our anhydrous. That's our number one goal for this. Yeah.
Hey, quick question for the lab. Did you find that their magnesium oxide was less than magnesium? Okay. What's that? Oh, for so the magnesium oxide value was their mass of oxygen, right?
Yeah.
Okay.
Yep. So we go back to this 100 gram total sample, and we look at this, and we need to figure out, okay, how much water versus how much anhydrous compound that we have. So I'm right here. I'm going to start with water. I always like starting with water in these problems. Our mass of H2O. In a 100 gram sample, if I'm given our mass of our hydrate, this one, our 14.25%, just becomes for us 14.25 grams of water. Okay, so I'm going to say, all right, 14.25 grams of H2O, which this whole chapter we've seen it. Grams, mass is nice to measure out in the lab, but we must convert this to our mole. So we'd say times, we draw our line, we divide by the molar mass of water, which is given at 18.02 grams for every 1 mole. And what we do here is this. I'm going to take 14.25 divided by 18.02, and I get a value. I'm going to go to actually 4 decimals here of 0.7908 moles of our H2O. All right. Okay, so we have that, which is the easy part here. And now we have to worry about our mass of our anhydrous. So what we're after is how much lead 2 acetate, number one, in grams do we have first. Okay, so I'm going to put this as our mass of our anhydrous substance here, which I'll write that down. Mass of our anhydrous without water. So in this case, we already know that we have 14.25 grams of water. We assume that we have 100 grams of our particular sample here. And so we do this. We take 100 grams total minus the 14.25 grams of and I'll label this, of our H2O. And so this allows us, if we take 100 minus 14.25, we get 85.75 grams of our lead 2 acetate. So I'm going to write that down, PB, and then our acetate ion in this case is C2H3O2, and there's 2 of those ions. We then say, all right, times, we draw our line, we cancel out on bottom by the molar mass of lead 2 acetate, which is 325.29 grams to 1 mole of our lead 2 acetate. And I'll take the time, write the formula down correctly, and we will then calculate here. So again, our numbers of importance here are diagonal, so they will divide. And so when they divide here, 85.75 divided by 325.29, I get, again, I'm going to go out to 4 decimals here, I get 0.2636 moles of my lead 2 acetate, my PbC2H3O2, and there's 2 of those right there. Okay, and now we do this. To find out what we're ultimately after is how much we should put, or what whole number we should put in front of our formula. So we're going to have our X, and we're going to take our 0.7908 moles of our water. Always put the moles of water in this case on top, divided by our moles of acetate, or our moles of our anhydrous, which in this case is 0.2636 moles of PbC2H3O2. And so when we do that and we calculate this out, again, we're taking 0.7908 divided by 0.2636, we get exactly 3, which is really nice. All right. So now here comes the answer to our question here, right? We wanted to ultimately determine, well, what is the formula? And I'm going to go one step further. I'm going to name this compound as well. So our formula here that we are interested in is going to be our lead 2 acetate, right? That's not going to change. The anhydrous is not going to change. PbC2H3O2, 2. And then remember, we have that dot to say, hey, water is attached there. We just took the time while we did this problem to say we have 3 of those waters. So we would put 3, and then we put, for water, H2O. Okay, now the problem doesn't ask this, but I do want to go one step further. The name of our hydrate here would be as follows. We would use lead 2 acetate. So I'm simply going to copy and paste that name from above. So we have lead 2 acetate. And then we have, again, 3 waters. So we would say tri for our 3, and then hydrate for our water. So the name of our formula that we just came up with would be lead 2 acetate trihydrate. All right, so this should give you a good basis to be able to complete the other problems from section 11.5, those in-class problems.